Hello and welcome to the third High Volt Web Talk 21. We are in the fall season. We are live in Dresden here at the headquarters of HIGHVOLT. It is exactly 2 p.m. Thank you for joining us. On the East Coast in the US, it's about coffee time. In the Asian region, it's about dinner time or the Feierabendbier. But we are here for you for this hour of discussion. With me is, as always, Dr. Uwe Kaltenborn, the Business Development Director of HIGHVOLT. Hello, Uwe.
Hello, Florian. I need to jump in directly and to correct you.
Yeah.
Also, if the weather in Dresden is in the moment that cold, it's not fall season, it's spring season.
Oh, right. You are so right. Oh, my God. I was already in the Oktoberfest modus, which is not taking place. Okay, spring season. Thank you very much.
You're welcome.
Apart from the weather and the seasons, we have quite some electric tools to have conversation with you. And therefore, I think it was pretty stable. The last session's Slido worked good.
Right. So therefore, also today you have two opportunities to join us for the discussions. We're expecting your questions. Either you use Slido. For that, we have prepared an outline slide, as you can see right now. So go to www.sli.do and you can access then our session with the hashtag WebTalk. There's also a QR code to go directly there. And as you know, there is still the chat function in YouTube, where we have then also two colleagues in the back office which take up your questions there and forward then the question directly to me.
We're expecting and looking forward to your questions. It's going to be a nice discussion about our this day's topic. But first of all, we have test equipment, of course, for cables also in the background. Beautiful designed. What do we see?
What we see here is between the two of us, it's a DC module worth of 200 kV DC, both polarities. So out of that we can build up then also larger configurations. So the largest one was 2.2 megavolt DC we have done in the past. And the large unit, maybe we can get the total view as well.
Oh yeah, it's pretty high.
So
11,
this is the WRM. It's an AC test system also for a cable manufacturer, which is actually through the factory acceptance test and on its way to the customer. So that will be dismantled in the next hours. So after we have finished the web talk, so the colleagues will continue to put all the things into boxes and to bring the system to the customer.
Because as we are live, we are in a full going process here in the working process of HIGHVOLT. And as you talked about DC cables, that was the topic in 2020. You remember when we had the session about DC cables, it was the session with the highest participation. And therefore we decided to continue this series and to bring in some new topics. Last time we discussed a lot about locating failures and the way how DC cable can be tested on site. Uwe, what are we talking about today?
Yeah, today we have invited three different experts, so that we can gain more insights in the topic of monitoring DC cables. So to do so, we like to get a deeper understanding about cable technology and especially extruded DC cable technology. And another point will be definitely to look into the evaluation of DC cable systems. For that, we know that monitoring is something always requested from the operator of such cable systems. Such a monitoring system, partial discharge measurement seems to be one crucial element. Nevertheless, DC partial discharges, we have discussed that already last year. That's something where conventional technologies have their limitations. And today we would like to discuss also completely new ways to handle that topic. Beside that, there's always the question how to evaluate such measurements and also to interpret and also to find a correlation to the real physics then in the cable. And this is the overall discussion we would like to take up today.
and with our expert, thank you, Uwe, that I'm gonna present you in the next minutes. We have two colleagues, two experts. They are connected via video line, as you say here. We have first of all in Karlskrona in Sweden. We say hello to Marc Jeroense. He's born in the Netherlands and living in Sweden since '97. He has previously worked in different roles at NKF, at ABB and NKT. He has a profound role in the development and commercialization of HVDC cable systems, and he acts since long at the interface of market and technology. Marc is an active member of the CEST, and he is involved in the world record of 525 and 640 kV extruded DC cable systems. And in his own consultant company, he's an active in giving services for cable testing, developing, testing, technical specifications, clarification meetings, cable system courses, and technical advisory. Hello to our round, Marc Jeroense.
Thank you very much for the nice introduction.
We're gonna jump to Markus Zink. He's located in Schweinfurt. Graduated in electrical power engineering at the University of Applied Science, Würzburg-Schweinfurt, and he was working some years in the field of superconductive magnets. In 2010, he joined ENBW Nuclear for his PhD on aging condition assessment of high-volt bushings. Since 2013, he is a professor at the FHWS for Electrical Power Engineering, and since 2019, he is leading the Institute for Electrical Power Engineering and High Voltage Technology, short the IEHT. He currently he researches on activities as he's much focused on HVDC applications and addressing the PD behaviors and under DC voltage and the electrical conductivity of dielectric liquids. He is member of CEST and VDE. Hello, Markus Zink.
Hello, thank you.
And with me live in the studio, which is very nice in 3 dimensions, Erik Winkelmann. He was born in Dresden in '87. In 2009, he received his diploma for the University of Applied Science in Dresden. Since then, he has held various technical positions here at HIGHVOLT Prüftechnik Dresden GmbH. His research focuses on the system theoretical analysis of partial discharge, measurements using real-time signal processing and machine learning. Since 2020, he is working on his doctorate at the TU in Dresden and the chair for cognitive system that is at the TU in Dresden. Hello, Erik Winkelmann.
Thanks for the introduction.
Good evening. Good afternoon. Evening in some parts of the world, definitely. Marc, we're going to start with you. Your first statement to this discussion today. The growth of HVDC cable businesses is at the start of beginning. HVDC, a challenging technology opportunity that is key for our future. That is what you say. So the first DC cable was installed in 1907. It is 114 years ago. It was for Moutier in France to Lyon, and it was a mass impregnated one. How was the route towards 525 kV extruded DC cables? Uwe had some slides with us, and we show the picture from 114 years ago. Uwe.
Yeah. So, unfortunately, the system as such, there are no real pictures available, but I found some 3 pictures to illustrate that. You can see René Thury, a Swiss engineer who was driving DC systems for railway, for trams in the cities, and he also has developed a Thury DC transmission system with motor generator sets based on DC. Unfortunately, the cable which was used 1907, there's no picture available. What I found was a picture from the from Deutsche Museum in Munich, where we see a 400 kV DC mass impregnated cable, which was taken only for a short time into service in 1945. So, and the cable must have seen nearly the same as we have seen here in the picture. Nevertheless, I think we should ask Marc how the technology was developed from there to the status we are discussing today.
for the introduction. Indeed, it has been a very interesting journey from the point of view of development. But let's start with the key enabler of this whole development, and it is the birth of the DC voltage generation and conversion, as you Uwe already started to mention. I think there are loads of people involved in the beginning of the century, the 1900s, but we could mention three of them. This is René Thury, as you said. You have Peter Cooper Hewitt, a US citizen who in the 1901 invented the mercury vapor lamp that was further developed into the mercury arc rectifier 1 year later. And then there's a Swedish guy called Uno Lamm, who's also a very important person into the further development of the HVDC converter systems. He was also placed in Southern California to make the Pacific DC Intertie project at 400 kV. So these were very important persons to enable the cables to be developed. And then what comes to the cables? And in the beginning of the 50s, at that time, one has reasonable conversion technology available. And one had AC cables, which were typically paper-lapped cable types. And at that time, there was no other type available. So it was really that simple, like, hey, we have a cable, lapped technology, let's try to put DC on it. And it seemed to work provenly very, very well up to today, because MI cables, which is a version of lapped technology, is still available. And some milestones are the Gotland cable in Sweden in 1954, which worked at 100 kV at 20 megawatts, very low as compared to today's possibilities. You had the cross-channel cables between France and the UK, the Contiscan cables, the Sui pole, now I'm talking about 450 kV already, the Sapei cable in Italy, which was at 500 kV at a record depth of 1.6 kilometers. And now we also talk about the NordLink cable between Germany and Norway at 525 kV and 1400 megawatts. And there's even a company who has type tested the cable at 600 kV of the MI cable type. Now, if we go back in time again a little bit and go to the 60s, then all of a sudden the polymer cables, the first polymer cables were developed, the polyethylene, even not cross-linked. And the same trick was done. Let's try put on DC. And sometimes it worked perfectly well. And the next trial, it was a disaster. And nobody understood why. And then it took many, many years to solve this matter. In the years between the 60s and the 80s, there were theoretical guys who said it has something to do with space charges. It sounds very mystical, and it means electrical charges in the insulation, in the space between the electrodes. And it took until the 80s and 90s, until the development of the space charge measurement systems. I think here we should mention Tatsuo Takada, a professor at the Musashi Institute of Technology in Tokyo, Japan, who developed several methods, the PA, PWP, LIP methods. Maybe we'll talk about that, I don't know. So at that point in time, the developments lifted off, and we had the first commercial project in 1999, again in Gotland at 80 kV, extruded DC. I think it was 50 megawatts. And then it was stepped up the successive years to 150 kV in a project in Australia at MorAlink. We had the Transbay project in the US at 200 kV, the Borwin 2 project first at 300 kV in Germany. In Alpha project between France and Spain at 320, we talked about 2 times 1,000 megawatts now, so we are, increasing in power as well. We have the Nemo project quite recently between France and UK at 400 kV, and now we talk about the very extensive corridor project in Germany at several gigawatts and 555 kV. And even we know that there have been systems at 640 kV qualified, and the laboratory examples are even higher. So this is the kind of historical development that we have seen in terms of voltages and the logic of going from paper to polymers. I think I stay here. There will for sure be more questions that relate more to the depth of the technology, and I will probably come back to that later.
Thank you, Marc, for this historical insight. Erik, the question to you, what was the development of testing method along this route, along this 114 years?
Yeah, on the left side we see here 85 years ago. The company was called Koch and Sterzel at the same location as we are today. And they designed a test system with already up to 1 megavolt DC, and followed by, in my opinion, a very remarkable finding in our historical archives is this mobile DC test system.
Oh, yeah.
We see there in the second picture, which was developed approximately 20 years later.
Pulled by horses, certainly.
Yeah, seems like it would, yeah, in 1956. And in the middle, we see a test system with up to 2.25 megavolt DC, which was developed, built, and tested here in the hall from which we broadcast today, back in 1973. And I think another remarkable test system located in the region of St. Petersburg in Russia was able to deliver a superimposed test voltage with a DC component of 1.35 megavolt and an AC component of 500 kilovolt AC.
Outside, very
in
interesting.
1980. Yeah, in the back you see a little a building where really people live in, so very close. And nowadays all these developments entered in the design of a modular DC test system, where every model has plus minus 400 kV DC and can be cascaded and even operated in parallel to deliver the required test voltage and test current corresponding to our customers' wishes, which Uwe introduced at the beginning.
Yeah. Thank you very much for also giving this insight here along the history. Markus, your statement for this round is, as the amount of HV cable installation, especially for DC voltage, increased rapidly, only a proper diagnostic is the key for a reliable and safe operation. Therefore, as well, a well understanding of the material behavior, especially within the complex insulation systems of joints and determinations, is quite essential. That's what you say. Materials and their electrical behavior are key for the reliability of cable systems. How can universities, as you work for, contribute to that topic?
Yeah, as Marc already said, the development started or getting pushed in the increase during that time when in Japan the new test possibilities were generated. So to measure these materials, to get more insight in the material behavior. And this is still a big topic for universities. So to make research, basic research, in the material behavior under DC load. Because as you remember the slides from Uwe, we now see a big jump in technology. So from 320 kV, where we already use such XLPE cables under DC voltage, now coming to 525 kilovolts and even more. And we need to understand the materials, the insulating system, how the materials play together, where are so-called space charges maybe, already were mentioned by Marc. Yeah, we have to measure this material behavior under DC load. Yeah, for the AC world, we use AC voltage more than 100 years ago. Also, the first DC experiences were more than 100 years ago. You mentioned it already, but now we are reaching a level in technology, such high voltages, you cannot transfer the behavior at low voltage to the high voltage level. And this is where universities have to contribute, where we have to do basic research to support the industry with material parameters, with a better understanding, with simulation methods and material research.
Thank you very much. Jumping to Erik and his statement for this round. Erik, advanced signal processing and machine learning bring partial discharge characterizations to a new level and as enables an advantage monitoring solution for expensive HVDC cable projects. So we are talking about really big data and artificial intelligence?
Yes, we are talking also about these so-called buzzwords. big data and artificial intelligence, in short AI. But to be able to use the methods behind these buzzwords, one has to do proper signal processing, intelligent signal processing. This means, for example, if you do a PD measurement like you know it, you just do it according to the standard IEC 6270. And what you do is with every incoming signal, you just determine a charge after a given rule, and you take this charge and you have a time where it occurs, and then you say, okay, in the AC case you get a pattern because the time is somehow correlated to the phase. In the DC case you just have time which is going on and the events which you determine the charge of. So the only feature you have for every signal which occurs is the charge. And this makes it, of course, hard to really find out the roots of this discharge signal. But still, we have to admit, or we have to say, that with only this feature, charge and time, we've done a lot. So we are able to assess the quality of components. Here we do it in our test field every day. And it's a very, how can we say, trustworthy method. And a lot of science and development has been done with this. But what do I mean with intelligent signal processing? In order to be able to find out more about these signals, we have to be able to fulfill two important tasks. The first is to reduce the data amount which we have at the sensor. So we have a very high sampling rate for PD, and we need to reduce this data amount. And we have to provide advanced features, so more than the charge, more than the time of occurrence. All this ends up in what we call big data. We collect the data. So now we are at the moment of the big data. And when we have the big data, we can combine it with metadata, for example, ambient temperatures, pressure, or data from the operation of the asset, like current, voltage, whatever, ripple on a DC cable, and so on. And now we are able, with this big data, with this intelligent signal processing, to use the methods which are behind artificial intelligence. And the aim in general is to gain knowledge which we didn't have before. So maybe to find out that some sort of PD only occur when the temperature is high, as a very simple example. Something we didn't even expect or we don't know before. And the constraint, one of the constraints is for all this, you can do this in laboratory or with a supercomputer or whatever. You want, in this time now, like Professor Zink said, we want to do this in real time. So the technology is advanced. Why shouldn't we advance also in the world of PD? Other sciences like neurosciences or speech technologies, they've done it already. So there is no reason why we should not do this in PD world or go this path also.
So definitely much more than buzzwords, using artificial intelligence, using big data and all this to get the step ahead, as we saw here the 140 years ago. Of course, the time is faster and faster. Coming to Marc, DC cables are established since a long time. We talked about this. What is the technical or the physical difference between AC and DC cables? Because they look quite nearly the same.
Yeah, that is completely correct. By the way, I still remember when I started as a young engineer that I couldn't understand that looking at this simple cable that it could be so interesting, which to many people I talk to is still difficult to understand. But if one looks at a picture of such a cable, maybe you can put a slide on screen here.
We bring it
but the AC cable to the left, the most obvious thing you see in this example of a submarine cable, that it has 3 cores, the 3-phase system. And the right-hand side, you see 2 examples of 2 technologies, which is a DC cable. Normally the plus and the minus cores, you have 2 cables per system. So 3 to 2, this is the most easy difference to see. But more to the heart of the matter, if one looks to the AC cable, it has what we call capacitive losses. So when you put an alternating voltage on the cable cores, it will generate its own current. And due to the ohmic losses in the conductor, it will heat up just by being a cable itself, just by the length. And the longer the cable, the more these losses are. So here you already listen and can understand there is a length limitation of HVAC cables. Also, the properties as described by the Maxwell equations is that if you have an alternating voltage, there will be induced losses in all the metal parts in the cable, further heating up the cable just by putting up voltage. This is nothing to do with the power that you want to transmit. It's just the cable itself heating itself up, and it diminishes then the useful current. So another way is that the electrical field calculations, the AC fields and the physics behind is rather easy, although the current rating is much more complex to calculate. If you compare that to the DC cable with its two cores, then you only have what we call the resistive losses, so the conductor losses, which is simply said there is no length limitation. Of course, there always is some limitation, but it's much more or less than AC cables. You have no induced currents that generate heat. On the contrary, here we have a very complex electrical field calculation that we have dealt with in the industry, and we have a simple current rating method. And in the graph, you see that if you want to have lots of power over long distances, you're on the right-hand side top corner of the graph, then you are in the DC regime, because there the AC cables are limited by their capacitive losses by the length. So even if you can reach rather long lengths, then it's only for lower power. So high power, like gigawatts, long lengths, hundreds of kilometers, then you go for the DC cables that you see on the right-hand side. Now, two examples, by the way. To the right-hand side of the cable, you see here a copper conductor with paper insulation, which is then for what I called earlier the lapped technology. And the newer technology emerged in the late 90s and onward is the extruded one, of which there are three versions. The DC XLPE, the high-performance thermoplastic elastomers, and the nanofelt XLPE.
And Marc, could you just shortly say some things about the special requirements in production of the cables, just shortly?
Yeah, very shortly. If we talk about these three categories of materials, DC XLP insulation, HPTE insulation, and nanofelt XLP, all of these materials shall have a very low leakage current and a very controlled space charge. So cleanliness in the factory, in terms of chemical cleanliness and physical cleanliness of the compounds of the materials, are even more important than compared to the AC voltages. Another thing which comes into existence, so to say, in the production of certain types of these materials, the XLPE versions, that they need an extra production step, the degassing, meaning you put lots of heat and ventilation on the cable, and it will, and some volatile components, some gases, as you could say, are removed from the insulation, and it increases the performance of the insulation. Now, a third thing I want to mention here is that an increased quality assurance awareness, I would think, is needed for production of these very high-powered cables. So these, I think, are the things that are special for production for DC cables of high power.
Thank you, Erik. What are the critical components, the cable system components?
Yeah, actually for DC it's a quite maybe not really solved question. For AC we know that the joints and terminations are mostly the parts where we have PD in. Usually the cables are produced, like Marc said, under very good quality conditions, and then in the field one has to build the joints. This is done by hand, so you can never assure that it's the same like any other, and usually the faults are in the joints or terminations. For DC we expect the same, but yeah, the corridor projects are aiming to be finished in 2025, 4, maybe 6, and yeah, so we will see what is happening. But everybody's assuming joints and terminations, I think.
Okay, Markus, shortly for you also this question before we come to the next point. What are the critical cable system components in your eyes?
Yeah. There are three components. We have the cable, we have the joints, as already said, and terminations.
Excuse me, Mark. Sorry. It was just the question to Markus.
Oh, Markus, sorry. Okay.
No problem.
Shall I answer? It's no problem. So also in my eyes, the cable joints, of course, they are quite loaded components because it is an insulation system consisting of different materials, different thermal electric behavior. And again, there's still a lack of understanding or deeper insight in the behavior of these materials or these material combinations at DC voltage. And one big part in the design and also in the operation is the temperature of these cable components. And there, the cable joints, you must imagine at this point where two cable parts are connected via such a joint, you have a thicker insulating system. Thicker insulation means also a better thermal insulation, so more temperature inside, more or stronger thermal electric effects, and we have to understand these effects, understand how the material reacts, and so on. Yeah.
All right. And shortly, Marc, to this subject, the cable system components, just what you wanted to start before.
Yeah. No, I think I just continue with what my colleagues have stated here. But I want also to add, I think that the industry is very much aware of the criticality of these components, for instance, the joints, or there are many, many parts in such a cable system. So the idea of joints is to have prefabricated joints that are well tested and hopefully also good quality controlled in the factory before it's installed in the field. And there, of course, that's the critical component. When you install it, there is some typical handwork. And there, whatever you can do to control that, both in the environment, the tooling, the procedures, and later on maybe also monitoring, it will help the function and decrease the criticality, so to say.
Okay, we're jumping to Professor Markus Zink. Space charge, Markus, behavior seems to be critical for DC cables. How do you evaluate them, and how can you transfer your results on thin film to a real cable?
Yeah, that's a good question, because now we are talking about the difference between basic research. This is usually done, as you said, on thin film material samples or material samples at all. And then we have to transfer this knowledge to real insulation systems. And in my eyes, simulation models are the key in the design of these insulation systems. And these simulation tools we must feed with the material parameters gained from laboratory sample measurements. And again, this is the part of universities, I think, to deliver the right way of modeling to the industry. So they can use the material parameters and the simulation tools to design their insulating systems. And then, of course, you also have to verify, the models by maybe real measurements on original sized mock-ups or so. So to have a control loop closed for your simulation models, of course.
And as we see, it's a very complex subject talking about this DC cables today, and it's about halfway through our web talk here. And I'm going to look to Uwe, and I think we have already via Slido and our chat function some questions.
Yeah, so I have collected the questions which are related to the first parts of the discussion, and I think I would like to add on the last comment from Marc. Are there any feasible and approved techniques for testing the condition of installed HVDC cable joints? So maybe Marc can tell us something about, or from his experience in his last years where he was working with this kind of technologies, and maybe then also Erik can give an insight what's available then also as testing techniques.
Yeah. It's, of course, a very good question, which is a very relevant question in the industry. I always want to keep close to the knowledge centers, which are the recommendations that are put out by CGRE or standards like IEC. I don't think we shall stop there, but it's a good starting point. There it's stated one shall do a proper after laying test which is often on a DC voltage test at high level, an elevated level during a certain time. That's the basic level, I think. Before we start to talk about more advanced methods, I want to mention again that it's better to avoid that anything goes wrong, meaning a really proper set of quality assurance and quality control methods when the joints are being made and being installed. Whatever you can do to reduce errors in the field by such proper methods is key before you go to the next step with more advanced methods. Because more advanced methods, I'm pretty sure we'll talk about next coming minutes or half an hour, is kind of the monitoring steps, or maybe an afterlaying test that uses an AC voltage and maybe even partial discharge measurements instead of the DC voltage, which is normally done for the DC voltage test. It must be said, though, and that's the difficult matter here, as soon as you talk about these DC cables, which inherently have long lengths and high voltages, once you need an AC voltage on such a system, you need huge generators, and due to the fact that you have many joints in these inherently long systems, you need many measuring points. So this is the difficulty, I would say, inherently in DC cable systems.
Yeah, thank you, Mark. So you have already answered then the way how to test it. So in addition to the DC test, it's something where we also supply test systems, as we have seen with WRVT as an on-site testing system. Where you then can also do an AC testing, including partial discharge measurement for the cable joints. So there's a second question. Maybe we can see also the slider questions there. And there's the question about indicators of a potential failure. And the question is there a chance to identify the change of the properties of the cable so that you can indicate when a cable starts to fail? So who wants to answer that?
Free choice.
I can start if you want me to. I think this is the kind of the holy grail. This is what one really wants to know. What can I measure? How do I link it to a physical aging process, whatever that is? And how can I measure when the thing will malfunction, which is another way of stating the lifetime of the system, the remaining life. I think there are, at least we can say, one can measure temperature. That's the kind of monitoring that exists today, the DTS systems, etc. Measuring partial discharges will be, of course, the topic being discussed in the next 20 minutes as well. That is less experience right now, but it shall, of course, not close the door. As Markus already told, there are things happening and there are new developments going on. But I want also to say that the idea that one can simply measure and link to physical properties and get an answer on the lifetime, it's really a good dream, but I think we are not there yet.
Giving the question to Markus, I would say, also.
Yeah, indeed. So partial discharge measurement can avoid that a failure develops and leads to a complete malfunction of the cable system. So it can be an indicator of there's something going wrong. So to have time to react and to search for the failure part and to explain maybe the malfunction cable part. But when we measure PD, there is already something going wrong. Another point is also the aging condition assessment by maybe dielectric measurements. So how to get an insight in the cable dielectric before you start PDs. But this is another topic. I think now we should focus on this discussion on the partial discharge measurements.
Mm-hmm. We jump on this now. Thank you very much, Markus. Uwe, I think we jump directly to Erik, to the question.
That would exactly then fit
Exactly.
to the next question to Erik.
Because PD measurements, Erik, on DC cable system, as we heard it from Marc, is the holy grail. You are claiming to have an idea to measure PDs on DC cables. What is your concept?
Thank you. Yes, we believe we have an idea to solve maybe all of these questions, or at least a big part of it. Maybe to explain where we come from. HIGHVOLT as a manufacturer of customized high voltage and high current test systems. Of course, we had a question here in-house. How can we, in the field, do a PD test on a late cable with this length? So, called the corridor projects in Germany. And how is such a corridor project designed, or what's the principal design? We brought a slide here. And usually you have a length of several hundred kilometers. Marc already explained why, because there the DC technology is very advantageous. And every approximately 100 kilometers you have the so-called cable transition stations. And the cables between these transition stations again are divided by so-called link boxes, which are placed every 10 kilometers. And because of the high weight of the cables, and you have joints every approximately 1 kilometer. And this means that you have access to the system only in a distance of 10 kilometers at the link boxes. And in between these link boxes, you have a lot of joints which could have a failure or might have a failure. We don't hope it, but it could be. And now the question is, how can you, with only those two access points, build up a reliable PD measuring system? And this brings us to the next slide. Therefore, the only possible place to install a appropriate measuring system is the link box. And now if PD occurs somewhere along this line, which is between these link boxes, one wants to know where does this PD come from and how high is it at the origin, so maybe even reconstruct the wave shape at the origin, so what's the spectrum of the PD at the origin, and maybe also what's the type of the PD, so do I have a void or whatever. And our approach, therefore, is to determine the transfer function between two link boxes, and so the cable segment between two link boxes. And therefore, we use special high-frequency current transformers to do both. First, measure incoming signals with a very, very high sensitivity, which we need to detect signals which are several kilometers away, for example, in the middle of this monitored element. And also to inject signals into the cable system in order to determine the transfer function between two neighbored link boxes. And when you do this, the signal propagates through the cable, so we inject something, it propagates through the cable, and due to the effects of dispersion and damping, it gets deformed. And this is what we know as a low-pass characteristic of a cable, also of an energy cable, so it's the same. And what we see now is the qualitative spectrum of a propagating pulse, which we measured about a year ago from a real cable and brought here. And what we do is we inject this pulse. We do this several times a day, maybe several times an hour, so it's not clear up to now. So to get rid of every influence like heating, aging, and so on, which could change the transfer function. And maybe this also answers a little bit this question. If the transfer function changes, we might be able in the future, by collecting data, we are again at the big data buzzword, and then using methods of machine learning or artificial intelligence to judge, okay, this cable is old or young. But if we don't start to collect all this data, combined with metadata, temperature, pressure, and so on, we will never be able to determine something and also to predict the future.
Thank you very much, Erik. And of course, collecting the data is one side. Markus, Zink, how can such a measurement then get interpreted? That's important. How do we get from or come from data to info?
Yeah, this is a good question, because in my eyes, it is important to get a feeling of the difference between AC behavior and now we're talking about DC. When we have a lot of experience in AC partial discharge analysis, but now we have to transfer all this knowledge to the DC world, and there might be very big differences in the influence of the partial discharge on the insulation system. In this slide, we can see something we did in our lab. So we had some well-known partial discharge test objects. They are called G1, G2, and G3. And now if we connect these parts maybe to a high voltage source, so we get partial discharge signals every second, let's say, and now we have to analyze. We have to develop algorithms to cluster signals that belongs together. So to build groups or boxes of signals, and then the next step will be to name these boxes. What is inside? Is this a corona discharge or a surface discharge, and so on? And then we can put this into our practical knowledge and say, okay, how dangerous is this now for the insulation system? And this is something we developed also together with HIGHVOLT to use artificial intelligence to do this clustering, for example. Mm-hmm.
Thank you very much. And Marc, coming to you, we're having the information now. There is a PD, so we recognized it. How does a system operator come to a decision what to do? I mean, he has to react very quickly.
Yeah, exactly. And I think I want to take one little step back in these monitoring systems. One must think in 3 steps. One have the systems, how of an example is described now by Erik and Markus. The system with the hardware, the architecture, etc. It's a quite complex system, and one also have to keep in mind the maintenance of such a monitoring system. I want just to put a kind of industrial perspective in it as well. So you put into place the system which has to be maintained. Second step, you have to gather all the data and you have to interpret the data. Now there will probably be generated loads of data. So this is big data and artificial intelligence, as you say, that must be used, because if you forget about it, if you just think, which is often the case, I buy the system, I'm ready, then it's wrong, because the data must be gathered, classified, interpreted. And that will be a challenge, of course, so that one must think into a holistic view there as well. Within that, one have to remember that in the laboratory it's much easier to measure the DCPDs. In the field, with all these electrical noise levels, it will be much more difficult. This is a challenge where more new smart technologies must help, because this is a challenge. And the third step is what you say, judge the status. Having your system interpreted the data, what shall the poor operator do? Shall he push the button on these 2 gigawatt links and put half Germany black or not? Of course, he will choose for his job and not push the button. So it's more probably into the direction of a maintenance scheme. If he sees somewhere in this system that indicates via artificial intelligence something might be wrong in this area along the link, it might be a signal for preventive maintenance rather than to act and to switch off the system. Yeah. Because we have to expect also in the next coming years, if such a system is put in place, very new, that there is not so much intelligence yet.
Yeah. Erik wants to adjust something.
Yeah, I just want to add one point to the topic of noise in the field when you measure a PD and you have to find signals and all these topics behind it. I would say they are in other fields in technology solved already. As an example, you have a Alexa speaker, you talk to him, and in the back your children are crying or whatever. So this is not really a problem which has not been solved. The only problem I see for this case is that you have a physical end of the cable itself. So when you look into the cable and the low pass characteristics, what is there from the signal, for example, 5 kilometers away? And if it is there, buried by noise or whatever, you are able to find this from a signal processing perspective. Just because people are always looking at PC background noise levels, but this is already information which is somehow calculated. Nobody looks at the real signals. So I had the case here in the test field, maybe as an example, that I could clearly see on an oscilloscope discharges, but after they were integrated according to the IEC standard, there was only noise. But I could clearly see them. So this is what's the problem, maybe.
Absolutely. And of course, we see this is really a very complex subject to talk about. And certainly some questions cannot be answered in this round. Of course, they will be answered then after this session here, definitely. But we jump in a final round of statements, I would say, Uwe. We have some questions, some short questions before, some answers before. Erik, very shortly about the cable, the big cable German projects here with several hundreds of kilometers of DC cable measuring each cable joint. What amount of data will be produced and how could you handle this?
Yeah, if you think of a really high performance measuring system, which you have to use in this case to fulfill all the things I told, so to find every signal below the noise, to extract better features, to enable more interpretation and characterization. You have like what I would say 250 mega samples, as we say, per second. So means 500 megabyte. I think everybody can do something with this number, 500 megabyte at least per joint. But this doesn't necessarily have to be a problem because what you first do is to get rid of all the noise. So in a normal PD measurement, you have like 50, 80, maybe 90% in laboratory, maybe 59% of the time there's only noise. You don't have to save this noise. And the methods Markus showed already, they enable to reduce the data amount drastically, because if you cluster it at the point of origin, so if you say, okay, there are 50,000 signals, but there are only 5 different types. So why should I deliver all the 50,000 signals? I just take of these 5 clusters, as we would say. I just take the best representative and send it to a system which is then determining the location and so on.
Yeah, and that means
so there are so many screws we can adjust to get the data amount really low, that this should be not a problem. And in the moment you can buy cloud space or whatever with little money, I have to say. So.
And you can, of course, be much more precise. Markus, Zink, to you the question. Do you see a chance to link all these information from the measurements to patterns related to physical processes?
Yeah, so I think the difficulty that comes from the point that the insulation system of the cable influences the signal itself. So that means from the point of origin of the signal to the point of measurement, the signal gets attenuated, as Erik already shown before. And this can be a big difficulty to distinguish then different types of failures. That is what you have to learn in some ways still. So it is not completely investigated yet.
Okay. Marc, quick question. Might that all be sufficient to estimate the impact of the lifetime of the cable system, which is also a financial thing?
Well, I don't think it will be the lifetime of the system, but I do think this could help to have an even better maintenance strategy and a maintenance operating system. When I said the Holy Grail, I really meant that you can calculate from all this data. I have 5 years left or so. I don't think that's going to happen, at least until I get retired. But a proper maintenance scheme is already so much value to know I have to act now, or I have to act within a year, or I don't have to act at all. That's already a big value. And I think that's how the industry should look at it. And I'm really happy to hear also from Erik that there are new methods going on to get better data and to reduce noise. Because I'm not trying to be negative here, but this is the starting point where the industry is, and that is the point you guys have to tackle and to convince and to get better.
Okay, last question before we jump in the questions from the chat. Erik, we talked about last time about failures and location failures. Is that still covered with the new monitoring system?
Yes and no.
Okay.
I have to say so.
Thank you for this clear answer.
Because if you want to reach this high sensitivity, which we talked about, you really have to at least couple to every link box, which is at maximum, as far as we know, 12 kilometers away, the link boxes. There you have to mount measuring techniques to appropriate measuring devices to have the high sensitivity for this 12 kilometers. But if you really want to locate a failure after a breakdown, then you have a very big signal, of course. So it's more or less a jump from operating voltage to 0. And for this, we don't need to measure every link box. So it would be, in case of a German German corridor project, sufficient to install this location technique in all of the transition stations and to equip every link box with a monitoring system for PD. And you can, of course, combine, or the final product will, of course, combine those features in one.
Okay. Uwe Kaltenborn has some questions at the end of our talk coming in via Slido. Uwe.
Yeah, there are some questions via Slido. I'm still struggling a little bit with the technique. Yeah, now it works. Can we get the questions on the screen? Yeah. I would like to start with the latest one. And yeah, there is the question, is the measurement system, Erik, an idea or is it already tested on a cable?
That's a very good question. What we often see in studies or in other publications is that you take a BNC cable and you say, okay, it's more or less the same to an energy cable and can do some measurements and some general findings. But we directly said from the start that we don't want to do something like this. We have a real cable test line here. We used only, so to say, medium voltage cable. But medium voltage cable in the sense of signal transmission, high frequency signal transmission, what we need for PD signals is even worse than HVDC cable. So we have calculated a factor of 2 in the damping. So we have here in our house the worst case scenario built up. And there we tested all our HFCTs, so high frequency current transformers, to inject the signals, to measure the signals and the algorithms as well. So this is more or less online, our cable test line, so our partners, our scientific partners can access it and can inject whatever they want or measure wherever they want and use this data to better their signal processing algorithms.
Yeah, maybe one question to Marc. How does the reliability of DC cables compare to AC cables? Is there a difference? I would expect there is a certain kind of difference because we also have different years of service for both technologies. So I think it's not so simple to compare.
No, you're right, Uwe. This is not easy, especially if we talk about the technologies to be implemented at the highest levels of the voltage and the powers. There is no data yet. What one can do is go to the data developed gathered by the industry in technical brochures of the CGRE organization. There are some data based on 150 and 320 kV systems that you're going to have to extrapolate in a way. These data are rather good. There are sometimes there is a way of going around this as well, and say you can say I can compare it with AC cable systems, but of course it does not give the real answer. But the practice so far, if you look at failures per year per 100 kilometers, is definitely not worse than AC cable systems. But the proof of the pudding is in the eating, and we have to wait until we'll see. But we can act before it happens, before the breakdown starts. And it's again by doing this measurement technologies to implement them, to be smarter, to have good quality control, and then one can push the numbers down. But there is at the moment no signal, I would say, in the direction that it would be worse than AC cable systems. But one shall be very careful because the systems carry much more power than comparable AC systems.
Thank you. Another question. Currently, IEC 60 to 70 discusses PD measurements under DC voltage by means of counting pulses. Is this a feasible technique to analyze discharges and criticality? Erik, I think that's a topic you have to take up.
Okay, thank you, Uwe. If one imagines a cable line like we have shown, so 12 kilometers, for example, long, 12 joints, and now you measure at one of these link boxes and you just count the pulses. What do you know? Exactly, you have no knowledge. You can count the pulses. You can say it gets more. You don't know if it's maybe noise which gets more. You don't know which joint is maybe the problem. You don't know where it comes from. You even don't know how high it is at all because you have the cable which damps and distorts the pulse. So could be that you have a resonance problem and you measure the double of what happens. It could also be that you have a damping. and you measure the half. And so what are you, as an asset manager, what can you do with this information? So the question will arise, where does it come from? Is it all joint 5, or is it all joint 4, or is it just noise? And you cannot answer this question if you just count pulses. So in my opinion, this doesn't really help. It's an indication for something, but also it could be an indication for nothing. Maybe to be so hard.
Yeah, so now I run into a problem because I already got a red flag from the back office that we are really close to 3 p.m. here locally. So nevertheless, and I saw the number of questions still increasing in the last minutes. I take that as a duty to think about another session on DC cables, most probably for the fall season. So therefore, I would like to close the session right now. Nevertheless, one or the other question we will directly answer then also in Slido, and some of the questions I would like to take with me and to come back with them then at the next event when we're talking again about DC cables. So back to Florian.
Thank you, Uwe. And of course, this is the flexibility that we can offer you, being live, planning new sessions. Of course, we're going in the final round of statements with our 3 experts for this round, starting with Erik here live in Dresden. Having a monitoring system with some artificial intelligence installed, can you imagine additional parameters or conditions of the cable to be identified and surveyed?
Yes, we really believe that it will be possible in the combination with big data and long-term measurements to get some information about the aging condition, and also to be able, what Marc mentioned, to predict in a certain plausibility. So to say, for example, there's a 60% chance that in the next 6 or 12 months this joint will whatever fail. So we suggest to change this joint in the next downtime, which is planned anyway. So just to reduce your risk. And this will definitely be possible in our opinion. And also, of course, in combination with the metadata I told before, so temperatures, voltage, current, and so on, one could also think about a better load management. So can I transfer some more power at the moment or not? But these are topics maybe for the future. So we focus on the PD recognition, localization, characterization at the origin, so the classification, which type of PD we have, and also, of course, out of this big data on the prediction of the future behavior of the whole system, which shall enable then the so-called word predictive maintenance, so that we can say, okay, we suppose you to change the joint for example, just to get rid of the risk.
And the whole community and of course the audience is always up to date by checking out HIGHVOLT website, and of course you can see here and get the latest information. Professor Markus Zink in Schweinfurt, what will be the focus on the academic research in the next years to come?
Yeah, as we have seen, the development in HVDC cable technology is quite fast, and I think beside the basic research universities usually do, we have the task to support the industry in their application-related research. So we talked about signal processing, for example, and signal analysis for this PD signal. So this is where we can support with our theoretical background the industry in their current development, also in the next few years, and I'm looking forward to that.
Thank you very much for showing up this network, and of course everybody can get connected there. Marc, Jeroense in Karlskrona in Sweden, what will be the further development of DC cables? What do you expect? Higher voltage, higher ampacity?
Yeah, that has always been a trend. I do think that in the next coming years we will have some kind of consolidation, stay at the levels we are at the moment, and get them implemented, get them out where they should be, and get good quality. But in the meantime, I think yes, there will be still next voltage steps. The C-grade technical brochures are developed for 800 kV. Larger cross sections of the conductors are being made. The lengths are increased. But so if we look at the time perspective, 2030, 2040, I think that's where it will be heading. But first, I think a kind of consolidation at level at where we are.
Thank you very much. Ladies and gentlemen, thank you to our audience. Thank you to our experts. Thank you to this live broadcasting here from Dresden. Uwe, it was quite dense and a lot packed in this hour.
Yeah, I think that's why I also stopped already then with the questions. A lot of non-answered questions still there in Slido, and therefore I think we should really take the topic up again. And I think also with the ongoing projects here in Germany, also around the world, we have other states where we also see that the topics come up directly then with DC cables. So nevertheless, we have the questions collected in Slido. You can also use our WebTalk email address to send us questions and also proposals what you want to know from us and also our experts or the experts we are inviting then for the next session. So when I look back for the last 1 hour, so what have we learned? We have learned a lot about open questions and also new inventions. So last time we were talking about innovation. That was mainly the meaning of how to make money out of good technologies and ideas. In the moment, we are still discussing inventions, going completely new ways. And that's something we need to overcome physical limitations. So when we're looking back 30 years, so Marc will probably agree, 30 years ago, telling some cable expert, yeah, we would like to go for an 525 kV DC cable based on extruded polymers, they would say, no way, ever. Nevertheless, the cable is there. It's state of the art. Even 640, there is a pre-qualified cable technology available. Today we are discussing partial discharge measurement under DC. With the conventional technology, we clearly have to state no way. Nevertheless, going beyond the borders and to link then also new technologies like the advanced signal processing and also advanced statistics, then we might be also able to make an innovation out of the inventions we have seen today.
Excellent. And of course, as you mentioned it before, we had some buzzwords here, but not used by Uwe, which is quite interesting. Why did you not use any buzzwords?
Yeah, so the typical buzzword is big data. So what means big data? Sometimes you can still put it on a USB stick in your pocket and you're discussing big data. I would like to discuss much more in the terms of data information and typically decision, so these 3 steps. But based on the discussions today, I would like to reformulate that data, information and the correlation to physics. That will be the key. And if you always talk about artificial intelligence, so where is the linkage to the intelligence we see in the human brain? Question mark for me in the moment. Whatever I have seen in that context, I would really call it advanced statistics in the first step, and maybe at a certain point in time, if we as humans cannot longer understand the algorithms, then maybe it will be artificial and maybe also intelligent.
And that is a proof that we still count on human intelligence, that we invite always human guests with Erik, with Marc, with Markus. Thank you to you two here to participate with your voices and with your brain and with your input. This is very helpful. And of course, Uwe, we have 2 things at the end. We have a nice video that we can show, I think, about the setup processing of our WebTalk.
Yeah, the making of.
The making of, and we have another information.
Yeah, so as I already started to talk about, there is a clear plan to continue with the HIGHVOLT Web Talks in September. And we are looking forward then to see you again within our discussion round here. And also from my side, thank you very much to all the experts which have participated in the spring season. A special thanks to all the people which were not in the view right now for
Absolutely.
you on the screen. So the camera crew there, the directors bureau in there, and all the colleagues here at HIGHVOLT which have or which made it possible to do the broadcasting from here, because we are really blocking here the working, and that means 2 hours or 3 hours building up, getting the whole thing down, doing the broadcast. So this is what the guys will then do overnight in additional working hours, and therefore also thank you very much for all the colleagues here in HIGHVOLT which have enabled that we could do this broadcasting. Then thank you, goodbye, and see you then for the fall season.
Thank you, goodbye from Dresden, and now the making of video.